I think we can start, otherwise it gets too late. This is a new Athena webinar. Let me welcome Sebastien Guillot from IREP, Université Paul Sabatier. Just to introduce him very quickly, although the community, I think most of you know him already. He did his PhD at McGill in Canada, and then he went for his first postdoc at the Pontificia Universidad de Chile, when then in 2018 was back to IREP as a postdoc, and now he is an assistant professor there and very involved in the NICER collaboration and in the SWAM collaboration. And he will present today the work he's doing for constraining the neutron star equation of state using X-ray timing and modeling of profiles. So we're very happy to have you here. So I leave you with your seminar, and thanks for accepting our invitation. And please go ahead.
Okay, thank you, Nanda. Thank you to the rest of the team also for inviting me to talk about this great subject. Feel free to interrupt me if the sound is a bit choppy or if the video is not fluid, and I'll shut off my video just in case the upload of my internet is not great. So yeah, I'll be talking about neutron star interiors and how we constrain them. So I'll talk about current results and upcoming or expected results of what Athena could do. So let's start with a bit of general introduction about neutron stars. They are extremely compact objects. You know, the step of compacity just before black holes. And because of this compacity, they can be used for studying very extreme physics. So we can study very extreme gravity when the neutron stars are inside binary systems. They have very high temperature, very large magnetic field, many orders of magnitude larger than the largest magnetic field we can reproduce experimentally. So we can really probe electromagnetism in a very intense regime. And the last point that will be the subject of this webinar is the extreme densities. Because of their compactness, the matter is compressed to extremely high densities, which make them probes of nuclear physics, of dense nuclear matter at very high densities. If we look at this sort of cutout of the interior of a neutron star, we see that, it can be separated in three main parts: an outer crust, where the nuclei are sort of layered by nuclear mass. The lightest element will be at the top, and as you go deeper inside the neutron star, the density increases, and you have nuclei that are more and more neutron rich. You have some electrons around just to keep your neutron star neutrally charged. And then as you go deeper, you enter the inner crust, and the nuclei become, as I was saying, more and more neutron rich. And at some point, some of those neutrons will drip out of those nuclei. So you have a sort of a lattice of material, neutron-rich material, surrounded by a superfluid of neutrons. And inside, deeper, is the core, where we essentially don't know much about the composition, the presence, the type of particles that are inside, and so on. So out of this neutron star, basically, we know the top 1 kilometer in terms of composition. The rest is completely unknown. And if we look at the fraction of the mass that this 1 kilometer layer is, it's a very small fraction compared to the entire neutron star. So really, we don't know what neutron stars are made of, and this is still a very important question that we're working on. This summarizes a bit what we know of quantum chromodynamics, with temperature on the y-axis and density of matter on the x-axis. So everyday matter, normal matter, let's say, is at the bottom left part of the diagram, where nuclei are made of matter is made of the nuclei that we observe, and so on. At high temperature, at high energy, this is the domain that we can study with particle colliders. On the top right part of the diagram is more the quantum Monte Carlo simulation that can study this type of matter. And if we look at the bottom right part, so low temperature, very high density, this is where neutron star may be sitting. And here we say low temperature because the temperature of neutron star is below the Fermi temperature, meaning that changing the temperature of neutron star does not affect the behavior of the matter. And so one of the questions is whether neutron stars are to the left or to the right of that transition line. So basically, are the quarks still confined within the nucleons, within the baryons, or are the quarks completely deconfined, and basically neutron stars should probably be called quark stars. In terms of physics, all of those questions can be described by an equation of state. So this is a relation between pressure and density of matter. So pressure on the y-axis, density of matter. And each of those lines that you see, or the gray band, represent different models of the equation of state that describes the dense nuclear matter inside neutron stars. So the pink is made of quark. The pink line is made of is a strange quark star. The red ones are nucleonic equation of state, so standard neutrons and a bit of protons. And the black ones are hybrid models, where they start nucleonic, and then at a given density, there's a transition of the phase of the composition into something more exotic. And so to go from the left diagram to the right diagram, we just need to solve the equation of stellar structure in a relativistic regime. And by solving this, we find that there's a single one-to-one correspondence between the pressure density, between the equation of state, and the mass-radius relationship for neutron stars. So if we can measure the masses, measure the radii of the neutron star, we can do the inverse step and determine which equation of state, which pressure density relation describes nuclear matter. So this diagram is similar to the previous one, except there are more curves. It's a bit of a more complete samples of a theoretical model. And it shows that basically we don't know anything. We don't know much about dense nuclear matter. And so it's very easy to cover this entire mass radius diagram. And the difficulty of knowing which equation of state is the correct one comes from two things. So first, we don't know the composition, like I was saying. Is it nucleons, or do we have quarks, maybe more exotic particles, hyperon, count, condensate, and so on? And the second aspect is that we don't know the strength of the interaction between those particles at those high densities. We have to extrapolate from the low density knowledge that we have, around 1 times the saturation density, so the density of a nucleus. We have to extrapolate to very high densities, so 3 to 5 times, up to 5 times saturation density. And the second thing that we don't know is, well, the second extrapolation that the second uncertainty that comes from this is the fact that neutron star matter is highly asymmetric. So large number of neutrons and a little bit of protons, but everything we can study in laboratories is closer to symmetric matter, meaning equal number of neutrons and protons. So this is also a difficulty. And so determining the equation of state is very important for neutron star astrophysics, but for a whole range of physics and astrophysics. In terms of nuclear physics, I talked about all the unknowns and the reason to really understand. It's kind of the missing piece of nuclear physics. And for astrophysics, determining the equation of state has very important implication for supernova explosions. What's the maximum capacity of the core of that exploding star before it goes supernova? It's very important for neutron star mergers as well, and the emission of gravitational wave that come into play. So as I was saying, we need to measure masses and radii. Here on this diagram, you see 2 masses that are shown as the horizontal band. Those are 2 high mass neutron stars, and those are the ones that give the strongest constraint. Measuring another neutron star with a 1.5 solar mass will not bring new constraint. We need higher masses every time, higher than any previous previously known mass to have new constraint on the equation of state. So on the left, you see a summary of a sort of recent summary of all the neutron star masses that have been measured. I won't be talking about this in too much detail because most of those measurements are done in the radio and not in the X-rays. And so this is an X-ray astrophysics talk, so I leave that aside. One thing to know about those masses is that they come with a wide variety of statistical uncertainties, and some of them are very large systematic uncertainties, and some of them are very difficult to quantify. And so this is why, despite having a lot of high mass neutron stars here, only a few of them are considered robust measurements that are being used for nuclear physics as a high mass neutron star. And on the right, it's something that I will be talking about, the fact that thanks to NICER, we can now measure the masses of neutron stars even when they are isolated, and I'll come into that later in the talk. So here's the outline. I have two main topics. Our first one will be constraining the equation of state by measuring the radius using a purely spectral method, so fitting X-ray spectra to deduce the size of the neutron star and the radius. And on the right, the second part will be this spectral temporal method, so what has been enabled by the NICER observatory. And so for both, I'll talk about where we stand, what are the current results that we have, the caveats that are involved with those two methods, and what Athena could be doing when we apply those methods with Athena data. So how well can the neutron star radius be measured with Athena using those two methods? And also I'll talk a little bit about how can Athena address the caveats that those two methods have. So let me start with the first one. If we want to measure the radius of a neutron star, the radius of an object, we have to observe thermal emission from its surface. This is important that the emission is thermal. This is important that the emission comes from the surface. We need to model this emission, obviously, choose the appropriate model for the type of neutron star that we observe. And we need to know the distance. And knowing the distance is very important because, as you can see here, the radius obviously is degenerate with the distance. So if the distance is uncertain with 50% uncertainty, your radius will necessarily be uncertain by the same amount. So which type of neutron star can be used? If we look at all the different types of neutron star that exist here in this magnetic field rotation spin period diagram, you see all the types of, well, probably all the types of neutron star sort of in a schematic way. And so we need to have thermal emission, like I was saying, from the surface of the neutron star. So that excludes most of the young rotation-powered pulsars. That excludes accreting X-ray pulsars. There's a lot of the emission that we see usually comes from either a disk of accretion and so on. So we'll focus more on the ones that have been circled. But then a difficulty comes with the high magnetic field of neutron stars. When we are looking at the thermal emission from the surface of the highly magnetized object, it's a lot more difficult to model. There are models that exist for magnetized neutron stars, but it becomes also difficult when, for very large magnetic field, the beaming of the emission at the surface will depend on the orientation of the magnetic field and so on. So if we want to have sort of easy to model thermal emission, it's easier to focus on low magnetic field neutron stars. And this is because the opacities in the radiative transfer, the opacities in the atmosphere, are dominated by free processes, and they are completely unaffected for magnetic field below 10 to the 10. So it's easier to focus on those objects. And I'll start quickly with low mass extrabinaries. So probably don't need to introduce low mass extrabinaries to people attending here. Neutron star accreting from a companion star. In general, those objects are, well, historically, they have been detected during accretion. The accretion disk and the accretion processes are extremely bright. But this is not what we want to see to measure the radius of the neutron star. We want to see the surface of the neutron star. So we look at those objects when they are in quiescence, when the accretion has stopped or significantly reduced, so that the neutron star crust that has been heated during accretion can finally radiate, and we can, well, it always radiates, but when there's accretion, it's the emission, the X-ray emission is dominated by the accretion. When there's no accretion, we can finally see the relatively faint surface of the neutron star with luminosity of 10 to the 32, 10 to the 33 ergs per second. And so we apply the method that I was discussing at the beginning, that we just need to apply a spectral model to this emission and deduce the size of the emission area. And so the size of the emission area is what we measure is this R infinity, the radius redshifted, affected by the gravitational redshift, so seen by an observer at infinity. And this is also very important because all the emission comes from the neutron star, coming from the surface is affected by its gravitational field. And so you see that what we measure is an observable that depends on the mass and the radius of the neutron star. The first of those objects, one of the first that was used for radius measurement was Centaurus X4, a known LMXB in the field of the galaxy, so a historical X-ray accreting X-ray binary, and it was observed during quiescence. And the spectrum during quiescence had a very nice thermal component. The distance was not super well constrained, but there was also a problem with that object. It's the fact that it has a fairly strong non-thermal component. And that non-thermal component could be, for example, a sign of residual accretion. And the presence of this non-thermal component obviously affects how well we can constrain the thermal component. And I think another issue with this one and similar object is that the non-thermal component is seen to vary. It is variable, so it is a bit complicated to accumulate a long exposure time with a thermal component, non-thermal components. But since then, thanks to Chandra, 20 years ago now, so I cannot say recently, but 20 years ago, Chandra started looking at globular clusters. And that's where we saw the really rich population of X-ray emitting objects. And among those emitting objects are some purely thermal, soft X-ray thermally emitting objects. And those objects are thought to be quiescent low-mass X-ray binaries. So low-mass X-ray binaries in quiescence, fully quiescent, they haven't accreted in a long time. And we see a pure thermal emission. They are extremely stable. Now we have something like 20 years of data for some of those, and their luminosity hasn't changed. Their thermal emission is still the same temperature. So it's really a sign of heat coming from the interior of the neutron star that has been, heated up by long and many episodes of accretion in its history. And now it's radiatively cooling, and we see that emission. There's no sign for any of the one that we know in globular cluster. There's no sign of accretion. There's no sign of non-thermal emission, and they have never been seen in an outburst as well. So it's a good way to say that we're sure there's no accretion, and we're almost sure that we see the thermal emission from the surface of the neutron star. And so if we apply some of those models for the surface emission of those neutron stars to the X-ray spectrum, we obtain those mass radius contours that I've shown. They come simply from the fact that what we're measuring is R infinity. And because R infinity depends on the mass and the radius, we obtain those sort of banana-shaped contours for those quiescent low-mass X-ray binaries. Something maybe obvious that I forgot to say, so I will say it explicitly. One of the advantages of globular clusters is that the distance are known very well and very precisely down to the few percent level. So this is a small uncertainty that adds up to the radius uncertainty compared to field low-mass X-ray binaries that might not be known with a distance that is as precise. Okay, so we have something like a handful of those quiescent low-mass extra-binary in globular cluster. They are listed here, 6 of them. Well, on this figure, there are 6 of them. And so each of them have their own contours with their uncertainty. And the question is, if they are all described by the same equation of state, so if it's the same physics for all neutron stars, what is the equation of state that goes, in a statistical sense, that goes through all of those contours to describe the dense matter? So there are multiple different ways to do this: statistical analysis, Bayesian sampling, and so on. What has been done recently is using a parameterization of the equation of state. So instead of testing a single equation of state and then going on to this next one, there's been some ways to represent the equation of state with some parameters. So either analytical parameterization of the equation of state by describing your pressure density relation by a series of connected polytropes, or there are also ways to parameterize in a physically realistic, let's say, way the equation of state. So this is some work that we have done with Nathalie Webb and Jérôme Margueron and a PhD student, Nicolas Bayot, where we use those 7 quiescent low-mass extra-binary and a physically motivated model of the equation of state, so parameterized, and we try to see which set of parameters of this equation of state was giving the best fit to all of our constraints. And so we ended up with this red contour here. So this is the best fit to the 7 quiescent low-mass extra-binaries. And so because we are using a parameterization of the equation of state, we can also represent it in a pressure density. And we found something that was consistent, for example, with the green band, which was from gravitational wave, the gravitational wave constraint of GW 170817. So now the question is, what about Athena? How well can Athena do for this type of method? So this is some work that I did back in 2015, trying to see how well Athena could constrain the equation of state using quiescent low-mass extra-binaries. So at the time, I had selected 7 quiescent low-mass extra-binaries for their low absorption. They had fluxes between 0.3 and 5 × 10⁻13. The distances of the cluster were between 2 and 10 kiloparsecs. And I selected them based on the criteria that there was no other source, no other X-ray source within 5 arcseconds. And this was for Athena's angular resolution at the time. And so the exposure time that were needed to obtain at least 50,000 counts for each of the sources were between 10 and 115 kiloseconds, a total of 450 kiloseconds for all of those sources. So 7 sources, 450 kiloseconds in total. There will be, clearly, there are some updates, simulation to be done, but here are the results that I obtained with the parameterization of the equation of state. So here, the equation of state was parameterized with polytropes instead of the realistic parameterization. And this was done, this was work done with Feria-Lozel. And you see that if you look at the red band here, the uncertainty, roughly the uncertainty on the radius was about between 1% and 2% at 1.4 solar masses. So a lot better than what we could do, which was closer to about 1 kilometer here. So closer to 10% with the current set of observational data from Chandra and XMM. Here we can reach a precision of 2%. This is quite impressive and really promising for Athena. One thing that is important that I mentioned is that Athena will not be able to resolve all of the QLMXBs in globular clusters. Some of them will not be resolved, and this is an example here of the core of the globular cluster M30, sort of downgraded at the Athena resolution. So all of those point sources that you see are sources in the globular cluster. The coalescent low-mass X-ray binary is the brightest one, but there are other sources that won't be resolved. Maybe one solution is to try to find quiescent low-mass X-ray binary in the field of the galaxy. This is quite tricky, but there might be ways to do it. So in terms of the sort of the to-do list for quiescent low-mass X-ray binaries to be observed with Athena, I think the first thing to do is to sort of reconsider the selection of quiescent low-mass X-ray binaries, maybe with a somewhat degraded angular resolution closer to 8 or 10 arcseconds. Here I show two examples. This is the core of the globular cluster 47 TUC. The quiescent low-mass X-ray binary is here. This one is another one as well. I downgraded the resolution basically to the XMM, and this was 5 arcseconds. So that source, if you degrade it to 8 or 10 arcsecond angular resolution, will probably not be resolved. There are other sources that are nearby, although they are not too bright. So maybe there are ways around. It. On the other end, if you look at this globular cluster, NGC 6397, the quiescent low-mass X-ray binary is shown by the purple arrow. And at the angular resolution of Athena, the source will still be fully resolved. So this source will still be a great target for Athena. So, like I was saying, all those simulations need to be redone with the most recent response matrices for WFI, and also we need to look at the benefit of the high resolution with XIFU. To do this work. Here, one of the issue not an issue, but one of the aspect of the modeling is the amount of absorption. You can at low resolution or at sort of CCD resolution, you can modify a little bit the absorption and compensate it by different temperatures, which means a different radius. If with XIFU, if you can measure the NH, the absorption very precisely with the high resolution, then you can sort of get rid of this degeneracy between NH and the temperature and the radius. And something else to do is to look into the possibility of for Athena to address the caveats that I'm going to discuss now. Okay, the first one, some of the caveats. Related with quiescent low-mass X-ray binary. Why do we only use the quiescent low-mass X-ray binary in globular cluster? I said it quickly at the beginning, the low-mass X-ray binary in the field of the galaxy, they may not return fully to quiescence. All of the ones that we see, there's even in quiescence, there's still some variability, there's still some non-thermal emission, which makes all of the modeling of the surface more tricky. So this is the reason why we look at the one in globular clusters, other than the distance. The other thing is that in the field of the galaxy, we are biased in terms of the low-mass X-ray binary we find because we can only find them from following an outburst. So they are in a state of accretion. Even when the accretion kind of stops, they're still active systems. The quiescent low-mass X-ray binary in globular cluster, we identify them because they're in a globular cluster and because we know the distance. Looking for just a thermal emission source randomly in the galaxy is a lot more tricky if we don't know the distance. An important question that is often asked is, what is the composition of the neutron star atmosphere? It can be hydrogen, helium, as I was saying at the beginning. All the elements at the surface of the neutron star are stratified by mass, so you will always have the lightest element at the surface. So if the neutron star has accreted in the past hydrogen from a companion star, hydrogen should be in the photosphere. This photosphere is 1 centimeter in height. It's the sort of the optical depth for that atmosphere. It's 1 centimeter. That represents a tiny amount of mass. But if the neutron star was accreting matter from a fully hydrogen depleted object, like a helium white dwarf, there could be helium at the surface of the neutron star. And so if we apply a neutron star hydrogen atmosphere model or helium model, the result that we get on the mass and radius are very different. And those are three recent examples for 3 quiescent low-mass X-ray binaries, where hydrogen at the top and a helium at the bottom hydrogen model and helium model at the bottom were used. And you see that the radius can change by 40 to 50%. This is radically different. And so this can be clearly problematic when we're trying to measure the radius of neutron star with percent precision. So either we can try to identify the donor star to know what sort of material was given in the past to the neutron star, if it was hydrogen-rich material or hydrogen-depleted material. Or we can try to see if we can determine this from the spectrum. At the current signal-to-noise spectra that we have, we cannot really differentiate hydrogen and helium. The differences are very subtle, and we can fit the spectra, the data with hydrogen or helium models equally well, and it's impossible to tell. It will just give you a different temperature, and if it gives you, for the same data set, a different temperature will just result in a different radius. I had done in the past some simulations to see sort of at which signal to noise, what number of photons from a quiescent low-mass extrabinary we would need to really be able to tell if it's a hydrogen or a helium model, and it's around 10 to the 6 photons. So at the moment, current data sets are closer to 10 to the 4 photons. And you see here the residual. So this is the data set for neutron star simulated with a helium atmosphere and fitted with a hydrogen atmosphere. So basically, if we were assuming the wrong composition, and you see that the red data set sort of is consistent, the fit is consistent with the data. So with 10 to the 4 photons, you can fit equally well helium and a hydrogen. But at 10 to the 6 photons, you can start seeing some structure, and you can start to probe really the subtle differences between those two models. Another aspect that could be really interesting is to have a clear measurement of NH, because a small variation of NH will sort of slightly affect your low energy sort of level arm of your thermal spectrum. So if you have a good measurement of NH, for example, from high resolution spectroscopy, then it will be easier to really determine the shape of your thermal spectrum. So you'll get the temperature better, and you'll have the radius. You'll measure the radius as well better. So there are some simulations to do with XIFU to see if getting NH from the high resolution spectroscopy would help, even if we cannot reach 10 to the 6 photons. Okay, the next aspect is whether the surface magnetic field is really negligible. There's no measurements for low mass extrabinaries in quiescence, because we cannot deduce the magnetic field if we don't measure, for example, the spin and the speed down of the neutron star. But if we compare the magnetic field to other low mass extrabinaries in the field, they are generally around 10 to the 8, 10 to the 9. So this is considered a safe assumption. I'll go on to the next one, which is an important one. Is the emission from the surface really uniform? Are we really seeing the entire surface of the neutron star? And the answer is we don't know, because we don't see pulsation from those stars, but we don't see pulsation because we don't look. This is because Chandra, which is usually used for observation of quiescent low-mass extrabinaries, does not have the time resolution to search for pulsations that are around, on the hundreds of hertz frequency. And so assuming that the emission comes from the entire surface, when in practice it's not, and there are some temperature anisotropy, could really lead to a bias in the radius that you are measuring. So this is a diagram on, a figure of the percent bias you could expect on the radius if there is a hotspot on the neutron star that you are not modeling. Okay, so if there's a temperature anisotropy that you're not modeling, how badly could you underestimate the radius as a function of the temperature of this hotspot? So obviously, if the temperature is the temperature of the hotspot is low, so closer to the rest of the surface, your bias will be small. But you can see that it rapidly goes down to 30, 40% if the hotspot is hot and you are not modeling it. The vertical line corresponds to upper limits on the pulse fraction, so basically on the possible presence of a hotspot for two low mass X-ray binaries, one in the globular cluster and the other one is SENX4. So can we really tell? Is there a way to tell if there's a temperature anisotropy or not? So the ideal thing would be to search for pulsation, like I was saying. If you have a hotspot at the surface of the neutron star and the neutron star rotates, you should expect variation of the X-ray flux. And for this, you need high time resolution because you need to search for rotation speed that are close to that are at the neutron star rotation speed, which you don't know, but you expect it to be in the hundreds of hertz for low mass X-ray binaries. You need a large collecting area because you need to collect a lot of photons to do those pulsation searches. And having a low background is also preferable. Like I was saying, Chandra cannot do this in a normal imaging mode, but one globular cluster was observed in timing mode, and it placed some upper limits on the pulse fraction of 1 QLMXB to around 16%. And so if we look at the current observatories, Chandra can only do this in timing mode, and the sensitivity of Chandra at low energy has decreased, so it's getting really hard to use Chandra for this, and the sensitivity of Chandra is quite low in comparison to other X-ray observatories. XMM could do this, but the angular resolution of XMM is not great for globular cluster, and when you use the timing mode in XMM, well, you lose your imaging capabilities. And the last one is NICER, which, okay, it's great, large collecting area, amazing time resolution, but the background is high and you have zero imaging. So we did try to observe a globular cluster with NICER, but basically you have tens of X-ray sources that can be fairly bright all within your field of view, and that we didn't find any X-ray pulsation. But the difficulty with NICER is that since you don't know your background, it's really hard to put upper limit on the pulse fraction. So this so Athena could really be doing this, has a decent angular resolution, low background, the time resolution that would be sufficient to search for pulsations. I'm gonna try to go a little bit faster now. Can we search for hotspot at the surface of the neutron star if the hotspot is always visible? So this is a question. If your hotspot is aligned with your rotation axis, and so basically you always see that hotspot, you would not be able to see X-ray pulsation, but can you tell spectrally if there is one or not? And so I had done some simulations here, looking at basically a hotspot with a slightly higher temperature than the rest of the surface, and looking at the exposure time that would be needed to really start to tell if there's a hotspot from the spectra alone. So basically you fit one, basically you look at the residual when you fit only one thermal emission model, and there should be two. And so you see that for reasonable hotspot size, you're around a few hundreds of kiloseconds to be able to tell if there's a hotspot or not. This is something that Athena could do, provided enough exposure time, but it's still somewhat reasonable. If the temperature difference between the hotspot and the surface is smaller, then the exposure time really explodes, and in some cases we need like 3 megaseconds to tell if there's a hotspot of 150 eV on top of a 120 eV surface. But this is doable. I'm going to skip that, and I'm going to skip a few things. All right, because I need to talk about NICER and the simulation of the pulse profile modeling with NICER. With Athena. So I probably don't need to go over the methods employed by NICER. Just hotspot at the surface of the millisecond pulsar. The temperature difference here is quite large compared to the what I showed for the possible hotspot on quiescent low mass X-ray binary. Here there's a factor roughly of 10 between the hotspot at the footprint of the magnetic field and the rest of the surface, and that when that hotspot rotates, it gives you variation of the X-ray flux. Okay, I'm going to go a bit faster. Sorry. And what we are exploiting with the NICER collaboration is the fact that the strong gravity of the neutron star makes the hotspot visible from the back of the neutron star. Simply, the zeroth order effect is light bending. And so the more compact the neutron star, the more you can see the hotspot at the back of the neutron star. For a neutron star that is less compact, so weaker gravity, the hotspot sort of disappears at the back of the neutron star. And so you see clearly that the light curve, the observed light curve, has a shape that changes depending on the compactness. So if you can model that light curve, then you can extract the compactness, meaning the radius and the mass of the neutron star. And so NICER has given us a beautiful data set, several megaseconds for several millisecond pulsar. I'm showing on the left the difference of the pulse profile between 130 kiloseconds of data with XMM Newton and what we can get with NICER in 2 megaseconds or so, 3 megaseconds, I think, for this one. So not only we have a slightly more sensitive instrument than XMM, but also you have an observatory that at the beginning was dedicated to the observation of millisecond pulsar. And on the right, this shows the pulse profile in phase energy. So the histogram in phase energy, just to show that it's not just the pulse profile that we're modeling, but it's the pulse profile at each for each energy channel that we model. So we put all this together, the data set, this phase energy histogram, a model for the surface gravity of the neutron star, which corresponds to the location of the spots, the amount of light bending in the metric, in the gravitational metric that we use. We use a model for the hotspot emission. I don't have time to go into the detail, but basically there's a few parameters for the size, the location, the shape of the hotspot, and we use an atmosphere model, hydrogen atmosphere model or other compositions. And the last aspect that we have to consider for NICER is a model of the background. And here I'm showing in orange the total data and the model, the sum of the model on top. Here, this is the non-X-ray background. Here, this is the sky background. So, and the thermal emission from the pulsar is here. So you see that in NICER data, the background really dominates, but we still have the count rate to be able to see the pulsar and its thermal emission. So we put all of this, having the background information is really crucial. We put all of this into a neutron star inference, a statistical sampler, and we get the mass and the radius. So you've probably seen those results for 2 millisecond pulsar. Just a reminder that there were 2 teams working on those analyses at the same time. So there's 2 papers for each of the two millisecond pulsars. The uncertainties are around 10% for each of the 2. There are still a lot of pulsars to be analyzed. JO437, this is the brightest one, a beautiful data set, quite complicated to analyze. This one was discovered by NICER. This one is a known isolated pulsar, so no mass known. I'm working with a master student at IRAP on the analysis of those 2 pulsars. One of them is a high mass pulsar, the other one, 0614. Was also the pulsations were also found by NICER, and it has a mass measured. Okay. Now, maybe the part that people were waiting, and time is running, and I'm very sorry. So, how well could Athena do for this for the type of method, the pulse profile modeling method? So we simulated the pulsar J0740 with the XPSI package, so the package developed by the team of Anna Watts at the University of Amsterdam, and we used the results of Riley et al. 2021 for this pulsar, so a radius around 11.5 and a mass of 2.08 with 2 circular hotspots. Okay, and so we simulated that for WFI and XIFU, 200 kiloseconds and 500 kiloseconds. So here we have the total count, the background in WFI. Remember, for NICER, the background was a factor of almost 100 larger than the pulsar. Here it's the other way around. And this is what the phase energy diagram looks like for this simulated source. And so we simulated that data set, and then we run the inference on the mass and the radius. And this is what it looks like. All of this is preliminary, and I'm going to have a lot of to be investigated in more detail throughout the rest of the talk. But we find that WFI in 200 kiloseconds could measure the radius with about 3% uncertainties. This is to compare with the 10% uncertainty of NICER in about eight times the exposure. So with NICER in 1.6 megasecond and WFI with 200 kiloseconds, we have essentially roughly the same number of counts from the pulsar. But Athena can do a lot better because the background is very low and the background is well constrained with Athena. Remember, NICER is non-imaging, so we can only model the background with large uncertainties compared to an imaging instrument where you can empirically determine the background. I'm showing here the NH, the amount of absorption that is constrained to about 20% compared to pretty much unconstrained with NICER. And this is just one single random noise realization of the data set. And so we did several realization, and all of them give mostly radius uncertainties with 3%. Occasionally, we have one realization that gives a radius a bit with a broader distribution. We need to try to understand why. Does it find another minimum, or it gets stuck somewhere? And something else that is a bit odd is that the distribution of NH can vary from noise realization to another. This is a bit odd, and we need to look at the entire parameter space. So this was for 200 kiloseconds, 3% uncertainty, and we also did it for 500 kiloseconds. And basically, we find similar precision, about 3% uncertainty as well with 500 kiloseconds. So here we could only do one random noise realization because all of this is quite expensive in terms of supercomputing time. So we should try to perform more noise realization to see if maybe this was just one particularly bad realization and all the other will be closer to, let's say, 2%. I don't have the answer to this question yet, so we'll see what comes out of it. So now keep in mind that this pulsar, JO740, is particularly faint. It's one of the faintest that we have observed with NICER. And so what happens for a bright pulsar? So we used the parameter of this JO740, except we put it at 200 parsecs. So it would sort of be similar to the brightest pulsar that we have. Here, instead of having 55,000 counts in 200 kiloseconds, then we have 2 million counts. So the data set is a lot better. We find precisions that are better than 1% on the radius. But there's an issue that we need to try to understand is that some of the parameters that we recover, the inferred parameters, are not consistent with the input values. So this is obviously a problem, and we need to try to understand what happened. Is the final likelihood similar to the input likelihood? Maybe we would need like a higher resolution run to see if we sampled the whole parameter space correctly, and so on. We need to investigate this in a little bit more detail. Now, let's look at XIFU. The time resolution of WFI around 100 microseconds is close to the limit of what we can afford for a 2 millisecond pulsar. That gives us something like 16 to 20 phase bin at most. Beyond that, we don't have the resolution is not well. We wouldn't be able to use more phase bin. So we looked at the XIFU, which is expected to have a better time resolution. So here you see that we have 22,000 counts for the same simulation of this of the JO740 pulsar, 200 kiloseconds with XIFU. We have less counts than with WFI. this diagram looks very, the data looks very scarce because there are a lot more energy channels, right? So there are a lot of spectral beam with just one or few or zero counts even. But when we look just at the spectrum, so all of this, all the phases collapse into a single bin. We look at the spectrum, we have still a nice spectrum that dominates the background. And the results for XIFU in 200 kiloseconds, we find uncertainty on the radius that are around 4 to 5% uncertainties, which is sort of consistent with the fact that with twice the amount of, more than twice the amount of counts, we had 3% uncertainty with WFI. There's a question here, the fact that we find an NH that is inconsistent with the input value. The input value was close to 0.06, 10 to the 20, and we find a value that is inconsistent with that. So we need to investigate this in a bit more detail. I would expect XIFU to be able to constrain NH fairly precisely from using, the edge, the absorption edge of the interstellar medium. We need to look into this, how this can be done. This should be done. And so why do I focus so much on NH? I've been talking about NH a lot, and it's because there is, knowing NH would help tell what is the atmospheric composition of the neutron star. And so this is a figure that I made from a larger corner plot with all the parameters, those giant triangle plot. I just selected the radius and NH on this, and you see three inference runs. One that was done for hydrogen, one for helium, and one for partially ionized hydrogen. And you see that each of the three give a different value of NH, inferred value of NH, and each value of NH results in a different radius. So if we would know the value of NH a priori, or if we could measure it from XIFU, that would be a great help to determine the atmospheric composition. I'm getting close to the end, and so this is the list of to-do for Athena post-profile simulations. So I'm going to reach my conclusion. Just to say that so Athena it could be very promising for the two methods that I presented. It will play a role to understand dense matter. Because of the very large effective area, the good timing resolution, the good spectral resolution. There are still a lot of things to do in terms of simulation, mostly looking at the new characteristics, instrument characteristics of WFI and XIFU. I guess one point that I want to make is that the key requirement for QLMXB, so for the method on the left, would be the angular resolution of Athena. For millisecond pulsar, the key requirement would be the time resolution. For both, a lower sensitivity than currently planned can be compensated by a longer exposure time because those two types of sources are extremely stable. So we just need to accumulate more time. They're not time variables. So other than the pulse phase, but on the long time scale, then they're very stable. So we can compensate by longer exposure time. And another requirement for two of those sources, for those two methods, would be good sensitivity and well-calibrated response all the way down to 0.1 keV. A lot of the information that we extract from those sources comes from below 0.5. Those are very small, low temperature emission. So if we can constrain that fairly well down to 0.1 keV, that would be great. And I'm done, and I'm so sorry for speaking for almost 50 minutes.
Thank you very much, Sebastien. It was extremely interesting. I have some questions, but would like to leave first the attendees to ask question. If you have a question, please raise your hand, and I will just open your microphone. Any question? Yes, Francis and Ilek. First, Francis, you are allowed to talk. Can you try?
Yeah, thank you.
Yeah, go ahead.
Yeah, thanks for the very nice presentation. I just had a small question regarding the quiescent LMXBs in the field you were talking about at the beginning.
Yeah.
I was wondering if you had, I mean, waiting for the arrival of Athena, if you had any insight on some methods to detect actually quiescent LMXBs within the field, because as you said, the ones that we see in the field are detected because they can enter outburst. Because I was wondering if we could have some actually quiescent LMXBs in the field, would be really interesting for Athena, because probably that the X-ray field is much less crowded compared to globular clusters. So it would be pretty interesting for the spatial resolution of Athena.
Yeah. So yeah, I did look into this. Very interesting question indeed. The difficulty with finding quiescent low-mass extra-binary in the field is that in all sky surveys or in sort of moderate signal to noise, you see a small spectrum, but you don't know the distance to the source. If you don't know the distance to the source, your spectrum can be the spectrum of anything. So it's really tricky. So I worked with 2 students on sort of cross-matching XMM data with Gaia data and looking at the point source that are in common, and trying to see if with the distance of the Gaia point source, which would be the companion star to the quiescent low-mass extra-binary, we could see well, we selected only the very soft, the softest sources and so on. So we did a bunch of selection on the XMM catalog sources, matching with Gaia, using the Gaia distance, fitting the X-ray spectrum to see if we found a temperature and a size that was consistent with a neutron star. There was a few candidates, and we need to look into this into more detail, but this is something that can be done and should be done in more details with XMM, with probably eROSITA when the catalog of sources comes out.
Okay. Well, thank you.
Yeah. Thank you, Francis. I have Ilek in line.
Yeah, thank you, Nanda, and thank you, Sebastien, for this great talk. I had a question concerning your slide in the middle of your talk, where you had these 4 panels, where you showed how you gather information from the observation, from a model of the radiative transfer around the neutron star. This one perfectly. Yeah. So you showed how Athena is going to bring much more precise measurements, but could you comment on the systematics which are introduced, especially about like the bottom right panel, so the ones concerning the emission model for all those spots? I'm really not familiar with this type of neutron stars, more accreting X-ray neutron star. Is it much simpler here, the hotspot parameterization? For instance, the size of the hotspot, is it something which is straightforwardly connected to the spin of the pulsar?
We don't connect the hotspot size to the spin of the neutron star. Although it could be there are some relation between the spin frequency and the size. We don't do this. We basically let it free and adjust it, infer it from the amount of pulsed emission. Does that answer your question, or your question was a bit more?
I mean, do you have other systematics in mind which could like provide inaccurate measurements with respect to our uncertainties on the modeling of the hotspot itself?
Yeah, so the approach that is being taken in a nicer team is that we start with 2 circular hotspots, and we complexify the model progressively, so allowing for a dual temperature spot, like you see on this figure, so like a hot core and a colder ring, or something like this, different shapes. And so as we complexify the model, basically we continue until there's no need to complexify the model further. Does that make sense?
Okay,
there is this
degeneracies.
So it's really hard to quantify. There will be a paper submit. I think it has been submitted. A paper on simulations using different spot shapes and how try to quantify this. A paper by a postdoc in Anna Watts' team. So look out for this one.
Okay, thank you very much.
Yeah, I would say that for some of the pulsar, it's fairly robust against different it's different spot shapes and so on. The result does not change too much.
Any other question? Otherwise, I'll ask you one. Just take the. First, let me wait if there are other hands. No. Okay. So I ask you a question. So do you agree, at least from your presentation and from what I studied in the subject, do you agree that we can consider the pulse profile modeling method compared to the spectral method that you showed, with, of course, having some systematics, for example, the emission pattern, the atmosphere, yes, but way more precise and somehow free of modeling assumption, not free, but way less modeling assumption than the other method. First, because we have the pulse profile, so we have an idea on the surface temperature map, which is something that we don't have in the other case. We know that there is no residual accretion because those are radio pulsars.
Yeah.
Many of them, we actually have the masses very well constrained from radio. So this is somehow one less freer parameters that you do have. So do you agree that if Athena should bet on measuring the radius, that's the way to go, not the spectral method? Do you agree?
I think so. So I would say that at the moment, the pulse profile modeling is definitely more robust for all the reasons that you mentioned and all the caveats that I talked about for quiescent mass extrabinaries. This is for sure. Let's say in 2035, when Athena flies, I think it would still be the case, but I think Athena has a great way to sort of free us of some of the caveats for quiescent low mass extrabinaries as well. Just by searching for pulsation in quiescent low mass extrabinaries, if we don't find any pulsation, then it's likely that there's no, the temperature is quite uniform at the surface. So then we are safe on this aspect, for example.
Yes, but they're in globular clusters, so there is always the angular resolution problem.
Yes, of course. Then I'll give you the field quiescent low mass extrabinary hopes. But I think overall, I agree. To answer your question by a yes or no, I would say yes. I agree that the pulse profile modeling is more promising and less affected by caveats.
Last question. Yeah. Do you think that, so if we compare this method of radio measurement with the most common and method in radio timing, where actually most common in the sense because we know this since 40 years that with radio timing of binary systems, binary neutron star mainly, you might hope to detect the moment of inertia, especially only for the double system, as far as I know. Although this was not measured yet, probably because the disappearance of one of the pulsars for several reasons. So do you think that those two methods in the next 20 years are the most compelling one and the only compelling one to measure radius of neutron stars? There's something else you would think of?
Well, I don't think we can put aside gravitational waves to constrain the interior. I mean, it's not the radius being measured, okay, but I think we cannot put aside gravitational waves. Yeah. The moment of inertia, I see this one, although it's extremely difficult, I see it as, from my understanding, although this is not something that I work on personally, but basically the only assumption is GR and that's it. There's no other assumption to simplify things. When it happens, it's going to be extremely reliable. I don't know what sort of uncertainty will come out, but it will be really reliable. And I don't think there will be a lot of red flags saying like, oh, what about this? Have you considered that or this? Just like we accept the Shapiro delay mass measurement as is, with their uncertainties that are purely statistical and almost no systematic uncertainties. I think it's on the same level. The moment of inertia measurement from radio timing is the same level of reliability as the mass measurement from Shapiro delay.
Thank you. Any other questions or comments? Or no, I don't see any other hand risen.
Okay.
Okay. If not, let me thank Sebastien again. Thanks a lot for the extremely clear, extremely nice seminar.
Thank you.
And hope to see you soon at the next webinar. I don't know if the community office has any announcement.
Yeah, the next webinar will be on 27th of April, okay, and will be given by Antonis Georgiakakis about forward modeling the energetic universe, okay? Thanks all for coming, and we hope to see you in a few weeks. And thanks a lot to Sebastien.
Thank you
for
very
this
much.
wonderful talk.
Thanks, Sebastien.
Thanks a lot. Sorry for being a bit too long. Bye-bye.
No, it was perfectly
Okay.
fine.
Bye.
Bye-bye.